Okay. So while we wait for everyone to fill in, let me go over just sort of where we're headed and any brief announcements. So okay. Just a couple of reminders. Your next homework is due tomorrow, 5-ish. Sooner I get them all in, the sooner I can publish the solutions. I have office hours today for an hour, and Tuesdays, just to remind you, I switched around the office hours. They're posted on the Moodle page. So I have 2 hours of office hours tomorrow, that in order to help people who are in ad lab, especially since there was a conflict there. But otherwise, I have either stupidly or wisely not chosen different ID names for any of my meetings. So anytime I'm in a Moodle meeting, you can catch me. So you might catch me in the middle of a department meeting. You might catch me talking to the provost. Go ahead. It'll be more interesting than almost any meeting that I'm in to be talking to one of you. So please do bother me. Anyway, that's the homework is due Tuesday, and then you have another set of homework that's basically on these next 2 chapters, chapter 8 and chapter 9. And if you look at the homework, it's somewhat reduced because like the previous homework, you have your next midterm a week from Friday, and it will cover these last 2 homeworks. There's a collection of sample problems, basically a sample midterm, in fact. And the midterm will go the same way that the last one did. You'll have 4 questions. You can choose 3, and you can use your book and your notes, but that's it. And you have all day to do it, but it's designed to be done in about an hour. We'll talk more about that when we get there. Okay. As for today, we are going to kind of, it'll seem like a detour, but it's not. We just finished about a week and a half going over ordinary differential equations, in particular, eventually second order ordinary differential equations. And now we're going to look at a special class, or at least a special manipulation of those, namely self-adjoint ordinary differential equations. And this sometimes comes under the rubric. I think your textbook actually calls it the chapter, the Sturm-Liouville theorem. And the basic idea here is that, again, trying to be creatively lazy. We're going to take a differential equation and we're going to recast it as an eigenvalue problem. And we love eigenvalue problems because we know, especially if we can take the differential operator, that is what our left-hand side of the differential equation is, and look at it as an operator if it's self-adjoint. In other words, if it's Hermitian, we know that the eigenvalues are going to be real, that they represent observables, and all of those things that you learned in quantum last year or this year, depending on when you took it. So it's a really neat way of looking at that, and it also has some definite applications, which we'll get into maybe at the end of today, certainly by Wednesday. So, and we've already seen these, especially in the case of the oscillator. I think your book generates, starts with an example of using the wave equation as a way of looking at this before it gets into the actual math of the Sturm-Liouville theory. All right, so, and then where it really gets beneficial is when you look at specialized functions, so the Laguerre polynomials, the Hermite polynomials, and all those things. Okay, so that's where we're headed. And I have done a bunch of, had to use scratch paper to do it, to fill in some of the gaps in your book's derivations. So we'll go through that today. But before then, we're going to do an in-class problem. Okay, And again, if you recall, what I'm going to do is break you out into groups of two. And I've gotten some feedback, and I really appreciate that. One of the feedback that I got, and I got that kind of um, on Wednesday, was to give you some more time. So I'll give you plenty of time to do this. The other bit of feedback, especially for these problems, because I want them to be practice problems, they won't always be at the start of class, but I want to kind of catch up with some of the stuff that we were doing, is to be very explicit about what it is that you need to use. What is the question asking? After all, these exercises are designed for you to get practice in recognizing in using these equations. Exams are kind of when, and homeworks too, for that matter, are when your first question is, well, what do I use to solve this? And then you go solve this. So I'm going to be explicit here. You're going to use the Wronskian method, which if you look in your lecture notes should be either equation d.29 or d.30, to find the second solution for the differential equation y double prime of x is minus k squared y of x is equal to 0. Okay, straightforward enough. You'll know if you got the right answer. We're going to assume that the first solution is e to the kx. So start with the ordinary differential equation form, and then find the linearly independent second solution. I'm going to start assigning rooms once I know everybody's written this down. So once you put your hand up in your response or whatever, once you've written all this down, you're ready to go. Yeah, or a thumbs up is good. Yep. Okay. Awesome sauce. Allie, are you ready? Okay. Nick, you ready? Okay, good. Let's start doing this. Um, oh, it's half on my screen, half not on my screen. Why is that? Okay. 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 Right. Okay. It's 10 after 10. Basically, it'll give you 10 minutes. All right, go. Okay. Okay. See, I think I unmuted myself. Was that better time wise? Okay. Now, um, you this is a solution to something that we've done before. So I'll just rather than asking, we'll just go to what the solution should look like. So obviously this is exponential solution, and so the other linearly independent solution would be the negative exponent. So the way that you go about doing a question like this is to recognize that we are looking at the general form of our second order ordinary differential equation with the p's and q's. That means that p of x is equal to 0 and q of x is equal to minus kx, or k squared. Right, so if we go to equation D30, which is the case for the Wronskian second solution without p, you see that uh, basically this y2 is y1 times the integral of this of dx over y2 squared. So I already wrote that 2x e to the 2kx prime in there. When you integrate that, again, you're integrating it over x. The lower limit doesn't matter, it just adds a constant, which you can deal with in terms of boundary conditions. We're really looking for the functional form of the second solution. And when you do that, um, you should get something that looks like this. In other words, our second solution, y2 is basically e to the minus kx. There is a constant in there, right? But we can take care of the constant depending on what since these are completely general, that constant could be equal to minus 1 over 2, right? If depending on what the solution, the boundary conditions are. Everybody get that? Thumbs up if you got that. Yeah. Okay. If you had trouble with that, make sure that you send me a note, or if you have questions now, you can ask. Are we all good? So you have in your homework something similar to this, where you're given one solution and you find the other solution. And on the practice exam, you're given something as well. Right? There are obviously more complicated things. We'll look at what happens with, say, Legendre polynomials when we talk about, when we get into self-adjoint ODEs and using the Wronskian to find them for different values of the different polynomials. Okay? All right. I'm going to go ahead and get to the lecture. All right. So, today, as I said, we're going to look at Sturm-Liouville theory, and we'll start, as we usually do, with some definitions. And the first thing is that we're going to consider our differential equation, as I said before, as basically with operator formalism. So we'll look at what's called the L operator. And later, when we look at Laplace transforms, we'll look at the D operator, and it's essentially the same thing. So we're going to consider our normal second order ordinary differential equation. The way we've written it, we'll do it a little bit differently for now, namely P0 of x times d squared y of x dx squared plus P1 of x d dx of y of x plus P2 of x. Okay. And you can recognize that if we divide by P naught, we'll get our P1 over P naught would be our capital P, and P2 over P naught would be our Q. Let's let L be defined as an operator, namely P naught of x times d squared dx squared. That's a square. So the actual operation of the second derivative plus P1 of x d dx plus P2 of x. And we're going to define it over, and this is a pretty important point, and it's often skipped over, that this is over the region A and B inclusive. That is, we're going to define our operator only in terms of this region, and that's because of what we're about to do with it, namely when we start to look at orthonormality with respect to these differential equations, because what we're doing is, in a sense, going back to vector spaces and things that we actually, if you want to, you can look at them in chapter 5 and 6 in this textbook. But in the interest of kind of carving out a week's worth of time of material in the move to this format of the class, I've passed over that because you've seen that recently in quantum. And this is more applicable in, this is completely analogous in terms of differential equations. If we do all of that, then we can write this operation as L operating on Y is equal to 0. It is an operator expression. Okay, so that's just how we're going to write these. And once we start talking about operators and vector spaces on a region, that means that where we're headed toward is defining problems in terms of eigenfunctions and eigenvalues, right? Which means that we need to be able to look at inner products. So we'll define the inner product. And here we'll switch formalism a little bit, and we'll consider, instead of y, u of x, because we'll want to consider, say, two functions u of x and v of x to see if they're orthogonal to each other. We can define the inner product using the same kind of broad ket notation that you used in quantum, namely u L u. We can write as u times the operator L operating on u, oops, and that's going to be defined as the integral from A to B of, in the most general case, the complex conjugate of u times L operating on u of x dx. Or in other words, u Lu is going to be equal to the integral from A to B of u and then P naught u double prime plus P1 u prime plus P2 u dx. Okay, so again, just using the same kind of formalism that you would have used in quantum, and taking off that, we can then define orthogonality for two functions v and u. How might we go about that? What would be the orthogonality statement?
Inner product is 0.
Right, so we would write v u right, is defined as the integral from a to b of v star x u of x dx is equal to 0, where, just to remind you what we're doing, u and v are solutions to L. And it shouldn't be surprising that, in general, if they're solutions to L and they're two separate solutions, they'll be linearly independent, they'll be orthogonal, right? And in fact, we'll be able to ultimately write them as, oops, eigenfunctions of L. And that's the whole goal here, okay? So in a sense, this is just sort of a recapitulation of some of what you've seen in either 160 or in quantum mechanics and other classes as well. You dealt with orthogonality um, in E&M. And in fact, this treatment of differential equations is what's at the heart of Fourier series, if you think about what goes into the Fourier series. All right. To complete our analysis, we need to define the adjoint operator. We'll call that L bar. And this is where, all right, you'll have to be patient. I think I got all the pieces down. Your book is a little opaque with this, but it was a fun night in front of the fire on Mother's Day. So I decided to integrate by parts about 4 times to get this right. Okay, so what we're going to do is look at the inner product of u and L operating on u, right? And use the definitions that we have available. We're just going to break this apart into 3 different intervals, okay? So this is the integral, and again, this is on the interval from a to b, which will be different for different differential equations. So from a to b of u p naught u double prime dx plus the integral from a to b of u p1 u prime dx plus the integral from a to b of u p2 u dx. Okay, those are just taking out the different pieces, and what I'm going to do is break these out into A, B, and C. C we're just going to leave as is. All right, so we'll start with A. So A, we're going to first integrate by parts once. So this is, and just ignoring for the moment the n parts, this will be u d dx of, oops, of p naught u prime minus u p naught u prime prime dx. And in fact, what we've done here first, rather than before we did integration by parts, was just recognize that d dx of p naught u prime is equal to p naught u double prime plus p naught prime u prime. So we just substituted those in. Now we're in a position to integrate by parts. We'll integrate this by parts. This gives us u p naught u prime evaluated at the endpoints minus the integral of p naught u prime dx this gives us minus u p naught prime u plus the integral of u d dx of p naught prime u. Okay, so that's just rewriting the integral into two different integrals, then integrating both of them by parts. That's this. This is then equal to u p naught u prime. I'm going to integrate this by parts. So that's minus u p naught u prime plus the integral of u d dx of p naught u prime minus u p naught prime u plus the integral of u d dx of p naught prime u. Okay, so far so good. We have some cancellations here, so that this then is equal to minus u p naught prime u, and I'll put in the explicitly that this is evaluated from a to b, plus the integral, and I'll just combine these two integrals now, of u d dx of p naught u prime plus u d dx of p naught prime u. This is all dx. But we can combine all of this so that this becomes minus u p naught prime u evaluated from a to b plus the integral from a to b of u d squared dx squared of p naught u dx. Yes, that's exactly what I wanted. B is a lot simpler. B, you recall, is the integral from a to b of u p1 u prime dx. That's equal to u p1 u minus the integral from a to b of u d dx p1 u dx. And then C, we're just going to leave that as the integral. So if we put this all together, we have that u L operating on u is equal to, we combine basically the boundary terms, u of x times p1. And remember, these p's are functions of x. So p1 of x minus p naught prime of x times u of x, evaluated from a to b, plus, and I'll write it in Bra and Ket formalism, d squared dx squared p naught u minus d dx p1 u plus p2 u, and then finish off with a ket on u. And this is a.7. Okay, so what we've done is just rearrange things. The thing that we want to notice is that all we've done is rewrite that first integral. What we want to do now is equate integrands in A.5 up page and A.7 which is what all of this integrating by parts is. And basically, I'm going to not go into the details of this, but you basically expand 8.7 and you compare term by term with 8.5. And what you end up with is u times p naught double prime minus p1 prime u. That is, you take this and you take two derivatives of that and chain it out. Right? That's where all of this is coming from. Plus 2u times p naught prime minus p1 u prime. And that all has to be equal to 0 for those two expressions, a5 and a7, to be equivalent. And from this, we get that the first derivative of p naught of x is equal to p1 of x. This is our condition for being self-adjoint. In other words, now we have we can write this as this, because the condition for 8.9 means that the terms evaluated on the boundary are equal to 0. Okay, so okay, so that's basically a big identity that we're going to use. I'm going to stop here, and you can shake out your hands. And if you have any questions, go ahead and ask them. It's a lot of math. But where we're headed is to try and make things as simple as possible. Okay? All right, so let's let L bar u be equal to d squared dx squared p naught u minus d dx p1 u. This is just taking out what's in this bracket up here, p2 u. This means that, there's another way of writing it, p naught d squared u dx squared plus 2 times p naught prime minus p1 du dx plus p naught double prime minus p1 prime plus p2 u. And that gets us to what we mean by a joint, namely, this operation is the same as that operation, right? Which is similar to what you've seen in quantum mechanics. When we talk about self-adjoint, right, what that means, is that the adjoint of the operator is the operator itself, right? So L bar u is equal to L u is equal to d dx of, let's call this now p of x du of x dx plus q of x u of x, where I'm taking the usual definitions for p naught, for p's and q's here. Where have we seen this? We've seen this. This is, or where will you see this? Linear oscillator, Legendre equation. These are the form. This is a way of describing these differential equations. We haven't said yet what we're going to do with them, right? All we've done, if you look up your notes, is we've taken the standard second order ordinary differential equation form, and we've shown that we can write it as an operator. We've shown that we can define things like orthogonality on in a region. And then we defined an adjoint, and now we can define or determine when an equation or an operator is self-adjoint. The last part to this is, what do you do if it isn't self-adjoint? And that basically requires use of a basically a multiplication factor. So let's let P naught prime not be equal to P1. By definition, that means that this can't be self-adjoint. We can make L self-adjoint by multiplying a factor 1 over P naught of x e to the integral over x of, say, P1 of x prime over P naught of x prime dx prime. Right. So in other words, the differential equation, or the differential operator, in fact, the differential equation itself may not be self-adjoint, but if you multiply through, and especially if you think about it, the way we started this is that we have the whole differential equation on the left side set equal to 0. So we have that freedom to multiply through this multiplication factor all the way through each term, right? It's still going to be 0 on the right side. So that means that we have, I'm just going to write this out sort of, what this gives us is 1 over P naught times this exponential factor, that's what's in the brackets there, times L operating on U of x is equal to d dx of this exponential term times du dx plus P2 over P0 times this exponential times u. And this is self-adjoint by comparing it to equation A13. And I think you have in one of your problems, it might be your first problem in this chapter, where you show that you can make one of the special functions, one of the equations that describe special functions, self-adjoint by using such an integrating or a multiplication factor. Okay. All right. So let's take a second and consider what we've done. Second order ordinary differential equation, usual form, right? And all we did was show that we can, by careful arrangement of the terms, make it essentially an operator that operates on a vector space. Right? Ultimately, we want to operate in something that's at least similar to the Hilbert space, if you remember that from quantum. If not, it's not a big deal. Where we're headed for is we want to get to self-adjoint operators, Hermitian operators, so that we can determine eigenfunction or eigenvalue problems that have real eigenvalues that then equate to observables when we use applications. Okay, but so far all we've done is a lot of math to show that that P and Q and whatever equation is equal to this operator formalism. Okay, any questions?
If you use the multiplying factor, is the exponential thing and the P2 over P0. Is that then your P and Q?
Yes. Yeah, and I think your book has an example, and I'll do an example offline using that. Yeah. Yeah, in fact, that's how it becomes self-adjoint. Yeah. Okay, I'm being mindful of our time, but I do want to get to the meat of this, which is taking this differential equation and making it an eigenvalue problem. And if you think about what's important about eigenvalues and eigenfunctions are cool and they're helpful, right? If we consider maybe your favorite, right? It's useful to know what psi is, right? But what's really cool about this is that, right? If we can get our, the point of this is if we can get our differential equations to look like operations like an eigenvalue problem, then what we may actually be after is not so much psi, but lambda, right? The eigenvalue, right? So that's why we're doing all of this. So this essentially is our first self-adjoint ordinary differential equation, if we're doing it in one dimension. And it's the stationary form of this that gives us our eigenvalue problem. The more general form would be, say, L operating on u of x plus lambda times w of x times u of x is equal to 0. Okay, so everything is important here. L is our operator. What's W? Also write this as L operating on U plus lambda W U. Well, what's lambda?
Eigenvalue.
It's your eigenvalue, right? So here's our U is obviously our eigenfunction or eigenvector, if you like. This is our eigenvalue. And W is our weight function. Okay. Why do we need a weight function? What's the weight function actually used for? You may have seen the way, I'm sure you've seen weight functions in quantum, but they may not have been called that explicitly. But they're really important in terms of determining one of the key value or properties of this eigenvalue problem.
Would that be like a H per or negative H per over 2m type of thing?
It could be, right? It is, but it is part of defining something, a property or an operation of two different eigenfunctions. Now, what can we do with two eigenfunctions? What's the thing that if you have two different eigenfunctions, what do you want to check first?
Orthogonality.
Right, you want to check orthogonality, and so how do you check orthogonality?
Multiply the bra and the ket together.
Right, in other words, you take the inner product. Right, now, the reason why it is not necessarily obvious is that for the Schrodinger equation, the weight is equal to 1. Right? And that's the same for the simple harmonic oscillator problem. So the weight is used actually for determining the inner product. Often the weight comes in, this weight function comes in with asymptotic forms. So forms where, say, the function, the value of the function at infinity when it doesn't go to 0. So we can define, say, V U in the most general sense for an inner product. This is true when you first learn eigenvalue problems, but most of the eigenvalue problems you looked at had a weight of 1, so it was kind of not obvious. It's the interval over that space that you're interested in of V star of x times U of x times your weight. Okay. And each of these functions or each of these equations have different weights associated with them in order to make their eigenfunctions orthogonal, right? And your book actually doesn't have a table for this, which I've found kind of weird, but that's fine. I'll give you a list of these before we go. So if we consider the different equation or situation, and we can write down for each of these, and this will be important for that first homework problem in this chapter, the associated P of x, Q of x, the eigenvalue, and then the weight that's associated with that. So for the Legendre equation, P of x is 1 minus x squared. If you look at the definition of the Legendre equation, you'll see that there's a 1 minus x squared in front of that first, or that double derivative. There's no Q of x. The eigenfunction is, depending on how you write it, L times L plus 1, and the weight is 1. Okay, so if you were to check two solutions or two eigenfunctions for the Legendre polynomial or for the Legendre equation and check their orthogonality, you wouldn't have to worry about weight. We'll see with Bessel equation, P of x is equal to x. Q of x is equal to minus m squared over x. The associated eigenfunction or eigenvalue is a squared, and the weight here to make these solution or these functions orthogonal is x. In other words, you need to have an x multiplied in that inner product. Laguerre, these are all equations or functions that show up when you solve either the Schrodinger equation or Laplace equation in different geometries. P of x is equal to x e to minus x. There's no q. Lambda is alpha, and the weight is e to the minus x. Simple harmonic oscillator. I'll let you guys do this one. What's P for the simple harmonic oscillator?
Zero.
So P multiplies the second derivative.
1.
Right, it's 1. And so Q?
Negative k squared.
Actually, I think I might have used a different, let's see.
Or positive k squared, sorry.
Yeah, so the way that so this becomes a little interesting here. We recognize that lambda, this q, is a different q from our original value of q. K squared becomes, because of the requirement for the solutions are eigenvalue, and our weight is equal to 1. So in this sense, let me make sure that I've written this down carefully. Yeah. I'm going to need to go back in my notes and make sure that this is careful. So I'm going to just put a star here. But you're right, it should be k squared, but the way that, in terms of the way that we've defined it before, but if we want to define what our eigenvalue is, it's what's multiplying the value of y. The weight in this case is equal to 1. We've been able to show that you can get orthogonality just by looking at the different eigenfunctions multiply or integrated together. And then I can fill out a table, or we can discuss other equations separately. I think that we're out of time, so I'm going to leave it here. Where we're headed next time is looking at how we use these to solve the Schrodinger equation. There's a particular example of looking at the at deuterium or the deuteron, and then some other specialized function solutions. So anyway, bottom line here for this is that we can take our differential or second order differential equation, make it a self-adjoint operator, and then use the tools that we've used for the self-adjoint operators to make eigenvalue problems that are generally easier to solve than solving a differential equation. So again, we're trying to avoid calculus. Okay, any questions? Okay, all right, well, I guess I'll see you guys later. I have office hours. If I don't see you then, send me emails too if you need help or you have questions about the homework. Make sure that you take a look at it. Again, it's due about 5 o'clock or so Tuesday. If you need extra time, make sure you email me, okay? All right, see you guys later.
Thank you.
Thanks, bye.
Yeah, bye.